Hello, and welcome back to the Cracking FAANG YouTube channel. Today we're going to be solving Leetcode problem 295, Find Median from Data Stream. The median is the middle value of an ordered integer list. If the size of the list is even, there is no middle value, and the median is the mean of the two middle values. For example, for array 2, 3, 4, the median is 3. For example, for array 2, 3, the median is 2 plus 3 divided by 2 equals 2.5. Because it's obviously an even length list, so we need to simply take the average of the two numbers that are in the middle. And the reason we don't have that for this one is because 3 is actually in the middle, whereas with an even one, there's two items which are technically in the middle. So we're asked to implement the median finder class, and this median finder is going to be initialized as a standard class, and it's going to have two methods. The first is going to be addNum, which takes an integer number and doesn't return anything. It's simply going to add the integer to the data stream stored somewhere in the data structure. The second method is going to be a find median, which returns a double, and what it's going to do is return the median of all the elements that we've seen so far. And we're told here that answers within 10 to the minus fifth of the actual answer will be accepted. Obviously, we're doing a median. If we have to do some division, that's why we have this little bit of leniency here. So that's the question prompt. Let's think about how we might solve this. So before we get to the actual best answer for this problem, there are a few other solutions that you could use to solve this problem. Now, you probably won't want to implement these in the interview because they're not exactly the most optimal solutions, but it's still worth bringing them up to your interviewer to show that you recognize that there are other solutions to this problem, and then you can actually talk about the pros and cons of each solution and discuss this with your interviewer before actually going with your optimal solution. You may think this is pointless, but actually it shows your interviewer that you are considering multiple solutions to this problem, and that you can pick one based on criteria. So being able to weigh the pros and the cons of a solution is a really good interview signal for your interviewer, because this is what you do in a real life scenario, right? There's gonna be multiple ways you can solve your problem, and they're each gonna come with their own pros and cons. So it's not just a pointless exercise to just jump into the most optimal solution. You don't actually have to code these inefficient solutions, but they are sometimes worth bringing up. And I guess good to know in case that maybe you forget the most optimal one, you can actually go with one of the suboptimal ones and at least get something down so they can, maybe give you some sort of, I don't know, credit for your solution. Maybe they're not looking for the most optimal. They just want you to solve the question. Anyway, I'm going to stop rambling. The most simple way to do this is simply to take the numbers that you're given. So let's say that our stream looks like 1, 9, 7, 2. What we want to do is the most simple way is let's just say that this is our stream. We'll just call it S, and then our internal data structure is just going to be a list. So first we get the 1, then we get the median, which is the 1, and then we get the 9, and then now the median is going to be the middle value here, and then we get the 7. So the problem with the 7 is that this list is no longer sorted, so we can no longer look at what the median value is. Remember that we can only look to the middle if the list is actually sorted. So our first solution here, which is kind of the inefficient one, is to be sorting each time, to just store it as we get it from the stream and then sort each time, and then simply just return whatever the middle value is. And then obviously sorting is going to be an n log n operation, and then to get the median is going to be big O of 1, because all we have to do is look at whatever the middle element is. So that's going to be each time we need to find the median, that's going to be what the runtime is. Obviously this is inefficient because we're resorting the list every single time. If we now got a number that would break this sort, then we need to add it and then resort. So this is why we don't want to go with this one, because we have to resort every single time. Well, you may be asking, okay, well, what if we don't have to sort each time? We've sorted it once. Can't we maintain this sorted structure? So let's say we have the 1, 7, 9 sorted, and then we get a 2, right? We don't have to just resort it. What we can do is, because this is sorted, we can actually use a binary search here to find where the insertion should be, right? We can basically do a bisection here to figure out where to insert it, and we can find that position. In worst case, of log n, because this array is sorted, and we could find the insertion point in log n, and then obviously to insert it is going to be big O of n. And the reason that it's going to be big O of n, because we need to insert it, right? So that means that elements, we put it here because it's going to be between 1 and 7, but then these ones have to get shifted, and because we're shifting elements in a list, that's going to happen in big O of n time, right? This is a standard array. It's not a linked list, so we can't actually insert something there in constant time. And then to actually find the median would be big O of 1 again. So obviously we don't want to do that because, it's quite inefficient. The big O of n is actually going to dominate this log n. So asymptotically, our runtime is just going to be big O of n. So obviously that's not great. Well, what is the optimal way to do this? And we want to achieve, ideally, we want to achieve, if possible, log n runtime in the average case. Now you're probably wondering, how in the world are we going to find a median in log n time, given that we have to maintain this nice structure? Well, here's what we're going to do, and the way that we're going to do it is going to be to actually use 2 heaps. And we will discuss how this actually works in a second. So I left you with a little bit of a cliffhanger there. I told you we need to use 2 heaps, but you're probably wondering, how in the world are we going to use 2 heaps to find a median? This sounds ridiculous. Well, let's think about what a min heap and a max heap give us. Remember that a max heap will give us what? In big O of 1 time, the largest element, right? In the heap. And then a min heap will give us what? In big O of 1 time, the smallest element. So how does this help us? Well, let's say we have some list with values. And what we're going to do here is we're going to have 2 heaps, right? We're going to have the max heap here on the left, and we're going to have the min heap here on the right. And what are we going to do? Well, in the max heap, we want to store the smaller half of the array. And in the min heap, we want to store the larger size of the array. So let's say we had the numbers 1, 2, 3, 4, 5, 6. So the heap here is going to have, 4, 5, 6, and this is just a rough drawing. And then the max heap is going to have 3, 2, 1. So why is this important? Well, if we can split it up evenly this way, then to find the median, all we need to do is one of 2 things. And the reason it's 2 things is because we can actually have an odd number. If in the case that we have an even number in our, min and max heap, so basically their values equal to each other, there's the same amount of elements, that means there's an even number, then remember, all we need to do to find the median, since technically, this list is sorted within these heaps, right? All we would need to do is take the average of this 3 and 4. Wait a minute, this just happens to be the top element of our max heap, and this 4 is the top element of our min heap. So to find the average, all we need to do is take the top element of our max heap, so this is going to be 3, and we're going to add it to whatever the top element of our min heap is, and then divide by 2, bam, we have 3.5 as our median. See why we use heaps? Okay, great. But what if we have, a 7 here? What if they're not actually equal? We're only going to allow one heap to actually be bigger. So let's just say that this is actually, like 7 here. In this case, we're going to make sure that one of the heaps always stays the bigger one. We're only going to allow one to actually have that extra element in the case that we have, odd elements. So we'll just say that the larger half is always going to have it. In this case, well, we can see that the larger half actually has more elements. So that means that the median is actually going to be the element here, the smallest in the min heap. So we can simply return whatever this element is. Cool, so that's how we actually find the median, and it's really simple, right? The problem is actually keeping these heaps balanced, because say we add something that breaks this structure, then we're screwed. We basically have to rebalance elements, and sometimes we're gonna have to move elements from the, this larger half to the smaller half depending on the next item that comes through in the data stream. And this is where the complexity of this problem is. But essentially what we want to do is when a new element comes in, we need to make sure, to figure out which heap it needs to go into, and also to rebalance the heaps so we always maintain this structure such that the smaller half of the array is always going to be in this max heap here, and then the larger half of the array is always going to be in this min heap here. And then this min heap can at most have one more element than the other side. And we're going to have to maintain that at all times. So that's really the difficulty of this problem. But if we're able to do that, then we can just solve it pretty standard. And then all we need to do is, again, actually finding the median is really trivial. It's the actual balancing of the heaps that's complicated. So instead of drawing this out, and as you can see, it's already messy, this isn't even a real example, we're just going to go to the code editor. I'll break it down line by line, and you'll see how we actually rebalance these things. I'll walk through the steps, and hopefully it should make a whole lot more sense. But essentially, just to summarize, we want to maintain these two heaps because we'll have access to these elements here at the top of both of the heaps, which will be used to actually compute whatever our median here is. So that's kind of the trick of this problem, is actually maintaining those two heaps. So enough talking, let's go to the actual code editor and write this up, and you'll see how brilliant this solution is. The first time I saw it, I was like, wow, this blows my mind. There's just some problems on Leetcode that do that. Anyway, enough rambling, let's go write the code. Okay, we're back in the code editor, and it's time to write the code. You're actually going to be surprised at how simple the code is for this problem, despite how complex it seems. We're using two heaps. We have to balance them to make sure that we have the proper amount of elements and the proper amount of numbers in each heap. But really, the code is like 10 lines. So let's get into it. Remember that we need to initialize our median finder here with two data structures. The first is going to be our heap of the elements smaller than whatever the median currently is. And the other is going to be another heap with elements that are currently larger than our median. So let's set those up. So we're going to say self.low is going to be equal to, an empty heap. And we're going to say self.high is going to be equal to an empty heap. And remember, low is going to be those elements that are smaller than the median, and high is going to be the elements larger than the median. And remember that we're allowing high to actually have one more element than low, because in the case that an odd, it has to go in one direction, and we're going to put it into the high for consistency. So when we add a number, remember that there's two cases that can happen. Either our heaps currently have the same amount of elements, in which case we need to add it to basically the higher heap, but we also need to do some sort of rebalancing, or we can add it to the lower heap and do some rebalancing. So let's do the case where they're actually equal. In this case, we actually want to put that element into the larger heap. Remember that the larger heap is allowed to have one extra element, so let's do that. So we're going to say if the length of let's go back. Apologies. So if the length of self.low is actually equal to the length of self.high, then what do we want to do? So we want to push our element onto the bigger heap, but we need to make sure that we're actually pushing the right element. So let's say we're going to heap push, and actually we should just call into the heap queue module here. They're all like imported globally in Leetcode, but just for good practice, we'll actually write out the module name. So we'll say heap queue.heap push. So we're going to put the value onto the heap with the bigger elements, but now we need to decide what to actually push onto there. Because it could be the case that our number needs to go into the smaller heap. And if it needs to go into the smaller heap, then obviously we don't want to put that number in there. We want to put it into the smaller heap, let the heap reorganize itself, and then what we're going to do is we're actually going to take whatever the biggest element of the smaller heap is, and we're going to put that into the larger heap. Because we want to make sure that we're always keeping those larger elements in the high heap. So what we're going to do here is we're going to push onto the heap of high. We're going to say heap push pop, and I'll explain this in a second. So we're going to push pop from the low heap whatever minus num is here. Now let me explain this because it's a little bit confusing. So in Python, when you use a heap, the default implementation is actually a min heap. There is an API for the max heap, but the method names are a little bit confusing. They all start with underscores. They're not easy to find. The documentation's kind of shitty. So typically what you do in these cases is you actually use a min heap, but you use negative elements, and that way it becomes a max heap. So that's why we have these negatives here, because we're working with the high, which remember is our min heap. We need to basically use negative numbers here. So that's the reason that we're actually using a min heap as a max heap. So that's why we need the minuses here. So essentially what we're doing is we're pushing this minus num onto self.low. And remember, self.low here is actually the max heap because it represents, the elements less than the median, and we need the largest element. So that's why we're using a max heap of the smaller elements. So since we're using a min heap as a max heap, that's why we need these minuses here on the actual self.low. So essentially what we're doing is, remember, the push happens first. So we're going to push minus num onto our low here. The heap will rebalance itself, and then we're going to pop whatever the largest element is. And remember, since we put numbers in as negative, when it comes out, it's going to be negative. So that's why we need to nullify that negative. So that way we can put it in as a positive into self.high. So essentially what we're doing in self.high is we're pushing whatever the largest element in this heap here is of the lows. So essentially we put in our element first, because obviously the push happens first, and then we pop whatever's at the top of the heap. And then we move that over to the high. So hopefully that makes sense. And that's basically how we do the rebalance in the case that they're actually the same size. Remember that we can always put that larger element into high. Otherwise, high is already greater than low. Then what we need to do is, in that case, we actually need to put it on... there's two cases. It can be either the case that high has that one extra element, or low has actually an extra element. So we need to actually move an element from the high heap onto the low one. So we're going to say heap q, heap, and again, we're going to be pushing onto the heap, except this time we're going to be operating on the heap of the smaller values. So we're going to be pushing onto the low heap. Basically, we're going to do the opposite of what we just did here. So remember, last time we were pushing onto the small heap. This time what we want to do is we want to push num onto the larger heap, self.high. Then we want to take out, once we push it, it's going to rebalance itself. And then what we need to do is simply to take out the smaller element and then put that into low. And that way we'll have that rebalance happen, and then we'll be able to maintain our nice invariant that basically that the low heap will have all the elements less than the median, and the high heap will have all the elements greater than the median. So let's do that. And again, we need these annoying negatives, because remember that the low is going to be operating as a max heap, but we're really using a min heap. So to do that, we're again flipping the signs. So we're going to say heap push pop, and we're going to do the same thing, except this time it's going to be operating on the high, and this time we're going to put num in there. And the reason that we don't use negatives here is because, again, the high is operating as a min heap, so we can just do it normally. We don't have to put minus numbers onto there. So to recap, we're basically pushing the number onto high, letting the heap rebalance itself, and then popping whatever the smallest element is, and the negative of whatever that smallest element is getting inserted into our self.low, which is our max heap of the elements less than the median. And that's the way we're going to keep our kind of invariant here going, so that way we can, find the median. So that's going to be how we actually implement add num. I know it's super simple. It's literally like an if-else statement. It seems really complicated, but you can do it in one line. It's ridiculous. So now all we need to do is just implement the find median. So remember, in the case where we have two numbers, the median is going to be the average of the two numbers in the middle. And then if it's an odd length, then it's simply going to be the number that's literally in the middle of our kind of sorted array here. And remember that in the case that they're not equal in lengths, then we just want to pop from the high. So that's going to be the value we use there. So let's do this. Okay, so we're going to say if len self.low equals to the length of self.high, then this is the case where they're equal. So we need to do that addition of the two elements and then take their average. So we're simply going to return float. of self dot high of 0, which remember is going to be the smallest of the big elements. And then we're going to say minus, and the reason that we're using minus is remember that our low heap here, we're putting negative elements into there, so that really this is going to be like minus whatever the number is, and then this is really just going to become a plus, so that's why we need the minus there. So we're going to say minus self.low of 0, so that way, we're taking the two elements at the top of the heap, and then we're simply going to divide by 2, and that's all we have to do. And in the other case, we just return whatever the element at the top of our high is, and that's it. So we're going to say return float self.high of 0. Cool. Let us submit this, make sure it works, and we haven't made any bugs, and it does. Cool. So what is the time and space complexity for our algorithm? Well, the time complexity here is going to be what? It's going to be log n. Why? Because every time we add a number, all we need to do is simply we're going to be just doing heap pushes and pops, right? That's all we're going to do, and they're going to happen serially. So in the worst case, right, we're pushing from the heap, we're pushing onto the heap, and then we're doing this heap push pop. So remember, to push from onto the heap, it's always going to be a log n operation because the heap has to rebalance itself in the worst case. Popping from the heap is always going to be a big O of n, big O of 1 operation, sorry, because we can always get the largest element easily. It's going to be in constant time. That's just a nice property of our heap. So basically, these operations are just going to be, big O of n, and then it's going to have, sorry, big O of log n is going to be the time complexity for add num. Obviously, for the find median, this is going to happen in constant time because accessing these elements from the heap here, we can just do it in constant time. We'll always have access to this in constant time. So this part is, big O of 1. So our, entire algorithm is really bounded by the fact that we have to do this heap rebalancing here on the two heaps, but that's just going to be asymptotically big O of n. Space-wise, if you think about it, all our heap is doing is storing the entirety of our data stream, except it's split over two heaps. So, in the worst case, one heap will have, we'll say big O of n divided by 2 minus 1, and then the other one will have big O of n elements, but asymptotically, this is just going to be big O of n because, we're just storing basically all of our elements in the data stream as they come in, and that's just going to be big O of n. So however long the data stream is, that's however many elements we're going to need. So that's your algorithm. Surprisingly simple. This is a hard level question. Some big companies, Amazon, Google asked this question. It's quite tricky. If you've never seen this before, to be honest, you probably aren't going to come up with the heap solution, but look at this. This is literally like if-else blocks to solve the hardest problem, and it's a one-liner. I think that you can easily memorize this. The intuition is actually quite simple once you've seen this before, so this isn't really one that you have to worry too much about. I think if you watch this video, you kind of understand how it works. Maybe walk through this part line by line if you don't exactly understand it, but essentially we're just moving elements around to make sure that our invariant stays correct, in that the low heap here is always going to have the elements less than the current median, and then the high will have the values greater than the current median. And then by simply doing these operations, we can maintain that median as we go along. So, and then this is how you calculate it. Really straightforward. Anyway, I'm going to stop rambling here. That was your solution for this problem, your time and space complexity analysis. If you enjoyed this video, please leave a like, comment, subscribe. If there's any videos you'd like me to make, please leave them in the comment section below. I'll be happy to make them for you guys. Just tell me the problem number, or tell me a topic you want me to cover, or just random questions about working in FAANG. What it's like, how much do you get paid, yada yada yada, all that stuff. I can answer it for you guys. Just tell me what you want to see. Anyway, thank you for watching. Have a nice day. Bye.